What's up, everybody? It's Miss Brothers. Just wanted to talk to you a little bit about this. This is page 2 of the thermal energy and specific heat practice, and this is all about reading different. We're going to say phase change diagrams of 3 different substances. Now, one of the things I want you to remember is that in chemistry class early on, we spent a lot of time dealing with the ideas of water, liquid water, frozen water, otherwise known as ice, and vaporized water, otherwise known as water vapor. And we deal a lot with the freezing and melting and boiling points of those substances. But what I want you to remember is that every substance has its own freezing and boiling and melting point. So for instance, the freezing and melting point of water is at 0 degrees Celsius. Its boiling slash condensation point is 100 degrees Celsius. And so we base a lot of our information about those things. But every substance has its own freezing and boiling and vaporization and melting points. And so one of the ways that we identify substances if we don't know what they are, is we look at their freezing or melting or boiling points in order to help us identify them. And we can also learn things about those substances if we know that information. So what you have here is you have a graph. And it might be a little bit hard to see on the video, so I'll kind of help you out. This graph, along the x-axis, we have time along the x-axis, and that's also another way of saying thermal energy, because we are adding thermal energy all along this timeline. And our time goes from a minimum of 0 seconds to a maximum of 300, well, 300 or more seconds. 300 is the last listed one, so we're probably going as high as 400 seconds. On the y-axis is our temperature line in Celsius, and it starts at negative 100 degrees Celsius, and here's 0 degrees, 100, 200, 300, and a maximum of 400 degrees Celsius. We have 3 different substances. We have substance A, which is this solid line right here. We have substance B, which is this dashed line, which is the dashed line right here. Okay. And we have substance C, which is the dotted line right here. So if we were to label these, this would be C, this would be substance B, and this is substance A right here along these lines. So there's certain things that we can see if we are questioned about these different lines. So let's start with question 6. It says, in the graph above, which substance has the lowest specific heat? Explain your reasoning. Well, if you remember, when we were talking about specific heat, I'm just going to go ahead and kind of write some notes around this sheet. What we know about specific heat is its definition. Specific heat basically is the amount of energy it takes to raise 1 gram of a substance 1 degree Celsius. And the lower the number, the easier it is, or the least amount of energy. So for instance, one of the things when we did that ChemQuest, we talked about the specific heat of a puddle versus the specific heat of a car hood. And what we determined is that if we have a puddle next to a car and they're both exposed to the same amount of sunlight for the same amount of time, what we decided as a group was that the car hood will heat up faster than the puddle of water. And what we figured out by doing that ChemQuest is that it takes less energy to heat up aluminum than it does to heat up water. And then what we determined is that the higher the specific heat of a substance, the more energy it takes to heat up that substance. So water has a high specific heat. So like if I had aluminum has a specific heat of like 1.89 joules grams degrees Celsius. Water, on the other hand, has a specific heat of 4.18 joules per gram degrees Celsius. And just by looking at the numbers, I can see that water has a higher specific heat. And what that means is that it takes more energy to heat water than it does. So in other words, it takes more energy to heat 1 gram of water than it does to heat 1 gram of aluminum. It takes 4 joules of energy to heat 1 gram of water, 1 degree Celsius. It only takes 1.89 joules of energy to heat 1 gram of aluminum, 1 degree Celsius. So in this picture it says, which substance has the lowest specific heat? Well, if we want to know, low specific heat equals heat up fast. And that's not well written, but in my head, low specific heat means it will heat up faster. So you're like, well, how do I possibly figure that out looking at this graph? Well, what you want to figure out is which one of these substances gets to 400 degrees the fastest. So for instance, this one, substance A, gets to 400 degrees in about 180 seconds. Substance B gets to 400 degrees in about 300 and looks like 20 seconds. And look, substance C hasn't even gotten to 400 degrees yet. So whichever one went the fastest has the lowest specific heat. So I'm going to say substance A. And I can say because, A, you can't spell because, it heats up faster than B or C. Now, if I were to ask you which one has the second lowest specific heat, you would say B, and which one has the highest specific heat, you would say it's C, because we haven't even managed, after all this time, we haven't even managed to get this up to 400 degrees yet. Okay? So we just answered question 7. List the substances from the table in order from the substance that will heat the slowest to the substance that will heat the fastest. So if we list the slowest, we know it's going to be C because even after all this time, we haven't even gotten to 400 degrees yet. So the slowest is going to be C. The fastest equals A, and the middle equals B. Okay? And again, which one heats the fastest? It's A. We've already shown that because it heats to 400 degrees in only about 180 seconds, A. And we could say that it heats to 400 degrees in 180 seconds. B heats to 400 degrees in about, we're going to say 310 seconds. And C doesn't get to 400 degrees in the graph time. Sorry if my handwriting is really sloppy. I'm just writing really fast. But so that's what we know. So we know that as far as specific heats go, A has the lowest specific heat, and C has the greatest specific heat.